So like I was mentioning in the first video, this is going to be really critical for people in the healthcare field, or even if you just have to go to a hospital. One of the reasons we actually give patients saline instead of pure water if they need an IV is because we want to make sure that we maintain the proper type of tonicity in their bloodstream. So let's say their bloodstream has let's say about a 6% solution of salt in it. When we add in saline, which is essentially salt water, we're adding in the same concentration so that we don't cause our blood cells to respond differently because they're in a bad environment, right? So we want to make sure that, as healthcare professionals, we do understand the rationale for adding saline into bloodstream to maintain the tonicity as opposed to adding pure water, which will dysregulate this percentage and cause those cells that are there to respond differently. The next type of tonicity is hypertonic. So you know what the word hyper means. Hyper tends to mean more. Think about energy, right? If you see the word hypertonic, that means we have more on the outside and less on the inside. So the concentration outside the cell is more concentrated than inside. So you see all these little dots versus 1, 2 on the inside. Okay. This is going to be an example of, let's say, 5% on the inside, 25% on the outside. So if we were doing our solutions, you might do something like 40% solute, 60% H2O. It has to be more on the inside. So that means the inside of this cell can be something like 25% solute and 75% H2O. This is like if you take a gummy bear, which is sugary, and you put it in a salt solution. There's more salt on the outside, less salt on the inside. That's kind of what this one is describing. What happens here as far as it relates to H2O? In this case, remember, water wants to maintain homeostasis. It wants to even things out. So let's say you're making a pitcher of Kool-Aid and it's too salty. Too sugary. What do? You have to add water to it. You have to dilute it. So what we're going to do in this case is water's going to move out. We're going to have the water move out of the cell, right? What is it doing? It's trying to dilute this concentrated area that's outside the cell. So as the water moves out, right, water's going to move out. What does that do? That causes your cell to get smaller and shrivel. So you normally start off with a cell because all of the water that you have is moving out to dilute this highly concentrated area outside. That causes your cell to now be much more shriveled up. It lost a lot of water, right? It's too much solute outside, all the water inside the cell left to try to help balance out that water in the solute concentration. This is one example why honey is known to be a food that will never rot or spoil or go bad. The reason is because honey is so sweet. If you had any type of, let's say, bacteria or cell that got inside of it, there's going to be more sugar on the outside, less on the inside of the cell. What happens to the H2O in this case? Well, all of the water is going to leave whatever organism that's in the honey, and it causes that organism to shrivel up and eventually die, right? So you never can have food spoil in honey because honey has such a sweet flavor. Hypotonic, if you've seen the word hypo means less. There's a condition called hypothermia where your temperature goes lower than it's supposed to. Hypo means less. So that means it is less concentrated on the outside. Again, less on the outside. We're always talking about the outside because we're referring to a hypertonic environment. And you know an environment is the outside, right? So hypotonic means it is less concentrated on the outside, more on the inside. So it looks something like this, right? Just a few little bit of solute versus something that's very concentrated on the inside. So if we did our numbers, it might be something like 30% solution or 70% H2O. And if there's more on the outside, then the outside might be like 5% solute and 95% H2O. So this is like a gummy bear in a freshwater solution. There's way more sugar inside of the gummy bear. So what do you think is going to happen to the flow of water? Which direction is water going to flow to try to dilute that area? Water is going to flow in. So in this case, water from the outside would move inside the cell. Same thing here, to try to dilute that highly concentrated cell. What happens here is the cell gets bigger. In an animal, it will explode. So this is going to cause it to explode. This is what happens when you put H2O in your bloodstream. So instead of putting saline, if you put H2O, it's going to cause your blood to look very dilute. And then all of the water in your bloodstream will start to go inside of your cells and cause them to burst, which is, not very good. In plants, they actually become really rigid, or we call that turgid. So plants have a special feature outside of their cell membrane called a cell wall. Hope you remembered. And that allows them to not actually burst. And remember, plants are, work with water a lot more frequently. They need water more. It's more essential. So this is one reason why they've developed that feature. Hypotonic. This is one way how pasta works, right? Pasta is going to be concentrated with starches, and you put it in a water solution. What happens? The water from the boiling water, the water from the pot is going to go inside of the noodle, and that's going to cause it to plump up. So this is also showing what happens in plants, just another visualization. Hypertonic, that means there's more on the outside, so the H2O leaves. Isotonic, it's in and out at the same rate. And then finally, hypotonic, it's going to flow inside of the cell. So this summarizes everything that we've covered as far as it relates to tonicity, right? That environment. An isotonic environment is going to have equal parts of solute on the inside and outside. Hypertonic, you're going to have a more or a concentrated amount of solutes on the outside, and it's going to be less concentrated on the inside. And then hypo is under, it's going to be less on the outside, more on the inside. So the environment is hypotonic, less on the outside. Again, looking about how this relates to cells. In a normal blood cell, we have a good concentration, a good mix. What happens here is if it is hypo, less on the outside, it causes an influx of fluid, which can either swell or burst your red blood cell. And then the opposite is if you have too many concentrations, right? Too much salt or sugar in your bloodstream, you can start to lose waters from your cell. This is kind of how it looks to be dehydrated right here. Again, this is just another image showing the cell lysing or breaking, the normal cell, and then a cell shriveling up. As I mentioned previously, when we talk about plants have this a little bit differently because they have the ability to shrink, but they do not explode. So if you ever get a question and ask what happens to the plant cell, do not say explode. Make sure you say expands or swells or gets larger, but they do not explode. An animal cell on the flip side actually can explode. So you can say it will burst, it will rupture, anything like that. So again, kind of reinforcing this idea, we have our active transport, low to high with energy, our diffusion, high to low, and then osmosis. We're actually looking at that water moving from an area that has more water to an area that has less water. And again, wanting to just show you a few of these images. You've already seen some earlier in the lecture or maybe in the previous video, but making sure you understand how to read this because we'll do this in class. And then we'll also look at something like this, right? Like a real patient sample. What is happening in patient A versus patient B based off of what we did. So my hope is that this was a useful lecture for you. If it doesn't make sense, please make sure you go back and rewatch it. And this will conclude the lecture for chapter 5.